Before a skeleton can support the weight of a human body, it begins as a mass of soft, unstructured embryonic tissue. Over time, these amorphous cells knit together, tightening into a dense, load-bearing framework. This specific biological process of forming bone from early connective tissue or cartilage is known as ossification or osteogenesis. To construct a complete skeleton, the human body does not rely on a single manufacturing method. It utilizes two entirely distinct biological pathways to engineer its rigid structures. The first pathway is intramembranous ossification. Here, bone is constructed directly from raw mesenchymal tissue, completely bypassing any intermediate structural steps. The second method, endochondral ossification, takes a more complex route. It requires the body to first build a pre-existing cartilage model as a temporary proxy before converting it into solid bone. Intramembranous ossification is reserved for structures like the flat bones of the skull. Long bones, such as the femur and the humerus, rely exclusively on endochondral ossification. The development of these long bones follows a strict 7-stage chronological timeline, beginning in the earliest stages of fetal development and concluding in young adulthood. Long bones require this intermediate cartilage proxy because a fully calcified, solid structure cannot easily expand from within. By starting with a flexible cartilage template, the bone can continuously lengthen during childhood while simultaneously bearing heavy biomechanical loads. The precise timeline of a long bone begins deep within early fetal development, long before any actual hard tissue exists. This reference text outlines the primary stages of endochondral ossification. The process begins with the formation of the cartilaginous nodule, as mesenchymal cells differentiate into chondroblasts. These newly formed chondroblasts quickly get to work laying down a soft hyaline cartilage proxy, a translucent blueprint of the future bone. This model is surrounded by the perichondrium, a vital membranous envelope that encases the entire cartilage structure. Once the initial model is established, the bone enters stage 2, the appearance of the primary ossification center. This primary center consistently appears dead center in the diaphysis, the main structural shaft of the fetal model. At this precise location, the cells within the outer membrane undergo a critical transition, causing the perichondrium to mature into the periosteum. New osteoblasts deposit hard matrix, forming a rigid bone collar that tightly wraps around the shaft. By tightly wrapping around the cartilage, this completely opaque collar physically restricts internal oxygen and permanently cuts off the nutrient supply. This creates an intentional mechanical and nutritional crisis for the trapped cartilage cells, forcing the biological sequence into its next destructive phase. Trapped within the rigid collar, the central cartilage cells rapidly swell, calcify, and ultimately die off. This is stage 3, known as cavitation, which leaves behind empty, porous spaces within the center of the shaft. These newly formed cavities provide the exact physical clearance needed for vascular invasion. Blood vessels pierce through the rigid collar and infiltrate the decaying center. The invading blood supply carries a fresh delivery of osteoblasts deep into the interior, where they begin laying down true bone matrix directly on top of the calcified cartilage remnants. The internal structure is refined in stage 4, creating the medullary cavity through osteoclasts. While osteoblasts build new bone outside, osteoclasts act as demolition crews inside. They remove central tissue to hollow the center, while the shaft lengthens. The timeline then transitions from fetal life to the postnatal period, triggering stage 5 of development. Usually after birth, secondary ossification centers appear in the epiphyses, the flared top and bottom ends. The structure of these ends differs in 2 key ways from the main shaft. The secondary centers primarily form spongy bone, and unlike the main shaft, they do not hollow out to form a medullary cavity. By early childhood, the long bone functions as a distinct 3-part structure. A rigid central shaft sits between 2 rigid ends, physically separated from each other by critical surviving bands of cartilage. This persisting band of cartilage separating the diaphysis and the epiphysis represents stage 6. It is known as the epiphyseal plate, or the growth plate. This reference lists the specific zones of the epiphyseal plate. This narrow structure operates as the sole microscopic engine driving the future longitudinal growth of the bone. The growth plate is a conveyor belt of 5 zones. It begins with resting cartilage, flowing into the proliferation zone where cells stack. In the hypertrophy zone, cells enlarge, then enter the calcification zone to die, finally reaching the ossification zone, becoming rigid bone. While this vertical conveyor belt governs growth in length, it does not explain how the bone maintains proportional width. Growth in thickness happens simultaneously through appositional growth. New layers of bone are added directly under the periosteum on the outside, constantly widening the shaft. This dual, biaxial system explains how a long bone manages its conflicting requirements. It can massively increase its volume and bear mounting biomechanical weight over a decade, all without ever compromising its structural integrity. As childhood ends and puberty begins, the timeline reaches its definitive conclusion. Stage 7, the fusion of the epiphysis with the diaphysis. The rate of ossification eventually outpaces the proliferation of new cartilage. The epiphyseal plate is entirely consumed, causing the isolated ends to permanently fuse with the mean shaft. Once that fusion occurs, the microscopic conveyor belt is gone. All vertical growth permanently stops. Because this 7-stage process operates as a tightly choreographed mechanical sequence, it remains highly vulnerable to disruption before that final fusion takes place. If a child suffers direct physical damage to the epiphyseal plate, such as a fracture straight through the cartilage zone, the conveyor belt can stall out prematurely, leading to severe asymmetrical growth defects. The calcification zone also carries a major metabolic vulnerability. A severe deficiency in vitamin D halts the hardening process altogether. Without that rigid matrix, the long bones remain soft and structurally fail under the weight of the growing body, causing the distinct bowing of the legs seen in rickets. Beyond local injuries or nutrient shortages, systemic hormonal shifts, like broader endocrine disorders, can slow or entirely delay the overall timeline of the ossification process. Endochondral ossification is a precise, decade-long engineering mechanism that dictates the limits of human scale, mobility, and long-term structural health.